So in this video I am going to prove why it takes 4 to 5 half-life for a drug to reach its steady plasma concentration. So to prove it mathematically, first take that in a very small time duration dt, the plasma concentration that decreases is dc. So dc by dt equals to negative kc. K is a constant and c is plasma concentration at that moment. It is like this because most of the drug follow first order kinetic. That means their elimination depends upon plasma concentration at that time. So C is during drug concentration at time t, K is elimination rate constant, and the negative sign means concentration is decreasing. Okay. Now next, after integrating both the side, we can get lnc equals to minus kt plus a constant. And you know, after even if you do not do this, if you just take the limits from t equal to 0 to t equal to t, you will get that concentration at time t equals to c naught into e to the power minus kt. That means concentration at time t equals to initial concentration into e to the power minus kt. From this, we have to prove another relation that at T half, plasma concentration would be half of initial plasma concentration. That means C naught by 2 equal to C naught into e to the power minus k T half. Sorry. And from that equation, we can get that half equals to e to the power minus k T to the power half. From that, taking log in both the sides, we can get finally k equals ln2 by T half. So we have two equations. First, at time t, plasma concentration equals to initial plasma concentration into e to the power minus kt, and another relation is this k equals to ln2 by t half. Now this is initial proofs, and this is the basic proof. On the base, it is the base of the proof I am going to show you. So the first dose is given at time equal to time 0. The second dose is given at time t. The third dose is given at time 2t. The nth dose at time into the power n minus 1 into t. So if you follow this trend, nth dose is administered. The first dose has been in the body for n minus 1 into t. So we are giving the drug in t in capital T interval. So when the nth dose is administered, the first dose, the drug that was given in first dose, is in the body for n minus 1 into capital T. Why this n minus 1 comes? Because if you see the number of doses, third dose is given at 2t time, second dose is given at capital T time. So n dose is given as n minus 1 into capital T times after the first dose as administration. So you get it. Now we have learned that uh, at time t, plasma concentration is c naught into e to the power minus k into t. So at this moment when nth dose is given, the portion, the amount of the dose that is remaining from the first dose is c1, the initial concentration that is given during first dose, into e, to the power minus k into the time duration throughout which this first dose and the amount the drug of the first dose is there in the bloodstream or in our body. And it we have seen that it is this time duration is n minus 1 into capital T. So when the nth dose is given, at that time the drug amount that is coming from first dose that is present in the body is C1 into e to the power minus k into n minus 1 into capital T. Similarly, the second dose contributes C1 into e to the power minus k into n minus 2 into capital T, and so forth. At the end, nth dose is contributing at this moment C1 amount of drug. So if you sum up all the amount of drug that is present in the body and take the C1 common, you will get the total amount of drug that is present in the body at that time, and it will be C1 into 1 plus e to the power minus kt plus e to the power minus 2 kt plus dot 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 plus e to the power minus n minus 1 into kt. This is coming from first dose, and this is coming from last dose, and this is geometric series with a ratio r equal to e to the power minus kt. If you sum up this series, you will get Cn equal to C1 into 1 minus e to the power minus nt 1 minus e to the kt. And what is steady state concentration? Steady state concentration is the when n, if we continuously at t interval give the drug for multiple times, for infinite amount of times, at the end the concentration of drug in the bloodstream will become constant, and that is the steady state concentration. If we if we make this n tend to infinity, in that case this Cn, this will become C1 into 1 by 1 minus e to the power minus kt, and this becomes the infinite geometric series up. So if we take the ratio of Cn and steady state concentration, then we will get from this equation 1 minus e to the power minus knt. So so in this equation you can see that fraction of steady state at time t, the fraction of steady state that we have achieved at time t is equals to nt equals to 1 minus e to the power minus kt. Expressing the terms of half-life t half, we have already proved that k equals to ln by t half. So fraction, after putting this value here, we can get the fraction that we're getting at time t is 1 minus e to the power minus ln by t half into t ln, and from there e to the power minus ln 2 we can get 1 minus 2 to the power minus t by t half. So putting t equals to first t half, we can get zero point 0.5, and after increasing the time, after fifth t half, we can we are getting the plasma concentration to be 96.875% of the steady state concentration. So effectively we required 5 t half to get to the to the steady state concentration. So interpretation is after 4 half-life, the drug reaches about 94% of steady state concentration. After 5 half-life, it reaches about 97. This way, 4 to 5 half-lives are considered the time needed to reach near steady state plasma levels.